Neutron stars are so extreme that they almost feel like mistakes in reality. The crushed hearts of dead giant stars, packed into a sphere no wider than a city, with gravity strong enough to bend light and matter, pressed close to the density of an atomic nucleus. In this video, we will drift quietly into their story, from the final silence of iron in a dying star to the supernova that exposes a remnant almost too dense to imagine, and finally to the collisions that may have forged gold, platinum, and other heavy elements now woven into our world. Before we begin, thank you for spending your time here. If this calm journey through the universe brings you a little wonder, please like, subscribe, and share the video. And gently let us know in the comments, what time is it, where you're watching or listening, and where in the world are you now? Let us begin with the life of a massive star before gravity wins. A massive star does not begin as an explosion, or as a corpse, or as one of the dense remnants that later make ordinary language seem too loose. It begins as a balance held inside a cloud of gas, where gravity gathers material inward and heat pushes back from within. The star is not solid, and it is not calm in the ordinary sense. It is a moving sphere of plasma, so hot that atoms are stripped into nuclei and electrons, so heavy that its own weight tries constantly to crush it smaller. Yet for most of its life, the star holds a kind of discipline. Gravity pulls every layer toward the center. Fusion releases energy in the core. Radiation and pressure move outward. The result is not stillness, but a continuous agreement between forces that would otherwise destroy the star in opposite ways. That agreement is the first quiet condition behind a neutron star. Before matter can be compressed into something nearly unreal, before a city-sized remnant can carry the mass of a sun, there has to be a long period in which collapse is delayed. A star spends its life resisting the thing that will eventually define it. In the core, hydrogen nuclei fuse into helium. This is the simplest and most durable fire a star can carry, because hydrogen is abundant and the energy released is enough to support the weight above it. Each fusion reaction is small, but the number of reactions is immense, and together they create the outward pressure that keeps the star from falling inward. The balance is delicate, not because it fails easily at every moment, but because it depends on fuel, and fuel is not endless. For a medium star, such as the Sun, the path after hydrogen is slower and less violent. The star swells, burns helium into carbon and oxygen, and eventually leaves a white dwarf behind. A dense ember supported by quantum pressure rather than active fusion. But a much more massive star carries a different future. Its gravity is stronger. Its core reaches higher temperatures, and once the easy fuel is gone, it is able to force heavier nuclei into new reactions. The star does not simply run out of fuel and fade. It begins to climb a ladder of elements, each rung shorter than the last. When hydrogen in the core becomes scarce, the inner balance shifts. Gravity presses the core tighter, and that compression raises the temperature. Helium can then fuse into carbon and oxygen. When helium is exhausted, the same pattern repeats with harsher demands. The core contracts again, the temperature rises again, carbon begins to burn into heavier elements, then neon, oxygen, and silicon follow in a sequence that sounds orderly only when spoken from a distance. Inside the star, each phase is more unstable, more compressed, and more brief than the one before it. Hydrogen burning can sustain a massive star for millions of years. Helium burning lasts far less. Carbon may burn for only centuries. Neon may burn for about a year. Oxygen may last months. Silicon may last only a day. The star is not aging gently at this point. It is rushing through the final options available to matter under extreme pressure. The outer layers may have expanded into a vast supergiant envelope, swollen far beyond the star's original size, while the center becomes smaller, hotter, and more crowded with heavy nuclei. The outside can look enormous, but the important story is narrowing inward, layer by layer. The star becomes like a furnace with shells of different reactions, each one surrounding the deeper core where the heaviest products collect. This shell structure is not a stable architecture in the comforting sense. It is more like a temporary stack of compromises, each made possible by the weight of all the layers above and the temperature of the layers below. Gravity is never absent from the story. It is patient. It waits behind every reaction, ready to take more space when pressure weakens. The star keeps answering with new forms of fusion, but every answer costs time, and each later fuel gives the star less time to respond. The reason is not only that the available stages are shorter, it is that heavier fusion becomes less efficient at supporting the star. The energy economy changes. The core has to work harder for less support. Eventually, this chain leads to iron, and iron changes the nature of the problem. Until that point, fusion can release energy because the products are more tightly bound than the ingredients. The star can build heavier nuclei and gain outward pressure from the process. Iron sits near the bottom of this energy slope. Fusing iron does not give the star useful energy. It demands energy. In the quiet accounting of nuclear physics, iron is ash. It is not dead matter in the everyday sense. But for the core of a massive star, it is the end of the road. The star has built an inner deposit that cannot help it resist gravity. This is the first real turning point. A massive star can look from the outside like an object of scale and power, but its survival depends on what happens in a core hidden from view. Once iron has accumulated there, the star contains a center that cannot burn its way out of crisis. The core keeps growing as silicon burning adds more iron group nuclei. The pressure of the layers above keeps bearing down. The temperature rises, but no new stable source of fusion appears to restore the old balance. What had been a sequence of recoveries becomes a trap. Gravity compresses the iron core, but the compression does not unlock another generous fuel. Instead, the core approaches conditions in which the familiar structure of matter begins to lose its ordinary resistance. Even before the final collapse, the star has become a layered warning. It still shines. It may still fill an enormous region of space. Its surface may reveal only the slow unrest of a supergiant. Yet at the center, the terms of existence have already changed. The earlier balance between gravity and fusion has turned into a countdown written in pressure, temperature, and nuclear binding energy. The last stable burning stage is not a prelude to another long era. It is the narrow bridge before failure. This is what makes the origin of a neutron star so severe. The remnant is not created by a simple cooling or a gradual shrinking. It is created when a massive star exhausts every useful way of holding itself open. The collapse that follows is sudden because the support fails at the place where support matters most. The star has been large for a long time, but the decisive event begins in a core whose fate is set by the inability of iron to give anything more. In that sense, a neutron star is not only the remnant of a supernova, it is the result of a balance that survived for millions of years and then reached an element that could no longer participate in the bargain. The beauty of the earlier star and the extremity of the later remnant belong to the same chain. The calm-looking main sequence, the swollen supergiant, the shells of burning elements, the hidden iron center, and the final loss of pressure are not separate stories. They are one continuous narrowing of possibility. At first, the star has time. Then it has hotter reactions. Then it has only brief reactions. Then it has iron. And once iron dominates the center, Gravity no longer has to wait behind fusion. It can begin to win without negotiation. The next stage is not merely a stronger squeeze. It is a collapse so deep that electrons and protons will be forced into a different arrangement of matter, and the ordinary architecture of atoms will be erased in the place where the star once made its light. Iron gathers at the centre of the dying star without behaving like a new beginning. Around it, other shells may still be active: carbon, neon, oxygen, and silicon burning in layers that once gave the star ways to delay collapse. But the inner core has crossed into a different kind of silence. It is not cold, and it is not empty. It is extremely hot, packed with nuclei, electrons, radiation, and pressure almost beyond ordinary comparison. Yet in the one sense that matters most, it has become unable to answer gravity. The earlier stages of a massive star's life were defined by useful burning. Hydrogen became helium and released energy. Helium became heavier nuclei and released more. Later reactions grew shorter and more demanding, but they still offered some outward support. Iron does not continue that pattern. It marks the place where nuclear fusion stops being a source of help and becomes a cost. The star has built at its own centre a material that cannot pay back the pressure needed to fuse it. The old exchange between gravity and energy breaks down, and the core begins to resemble a sealed room whose walls are still closing in. The reason iron matters so deeply is written in nuclear binding energy, a measure of how tightly protons and neutrons are held inside atomic nuclei. Lighter elements can release energy when they fuse, because their products are more tightly bound than their ingredients. The star gains support from that difference. But iron group nuclei sit near a peak of stability. Pushing them into heavier forms does not release the kind of energy a star needs. Instead, it consumes energy. For the core, this is not a minor inefficiency. It is a terminal limit. Gravity continues to press inward because the mass above the core is still enormous, but the iron itself cannot ignite into a generous new fire. The star has not merely run out of one fuel. It has arrived at a substance that turns further fusion into a losing transaction. As silicon burning continues in the surrounding shell, more iron group material is added to the center. The core grows heavier, its temperature climbs, its density rises. Under less extreme circumstances, pressure from electrons helps resist gravity, because electrons cannot all be squeezed into the same quantum state. This is one of the strange rules of matter at small scales, and in a white dwarf it can support a stellar remnant for immense spans of time. In the iron core of a massive star, however, the burden becomes too great. The electron pressure is not weak in any familiar sense, but it is finite. The core approaches a mass where the electrons can no longer hold the structure against the inward pull. The failure does not require the whole star to understand what is happening. The outer layers may still be vast and luminous. The center alone has to lose its footing. Once that happens, the rest of the star is forced to follow the consequences. The iron core is therefore not a passive lump waiting for collapse. It is an active limit being pushed harder and harder by the star that made it. As compression increases, another process begins to steal support from the core. High-energy light can break apart iron nuclei in a process known as photodisintegration, where photons carry enough energy to undo some of the nuclear assembly that earlier burning had produced. This is a severe reversal. The star once released energy by building nuclei upward. Now, under extreme heat, energy is consumed by tearing them apart. At the same time, electrons are driven into protons, forming neutrons and neutrinos. Each of these electron captures removes particles that had helped provide pressure. The core is losing support in more than one way at once. It is not simply being crushed from outside. Its internal means of resistance are being dismantled by the very conditions created during its final compression. The neutrinos produced in these reactions are extraordinarily difficult to hold. In normal matter, they pass through almost everything as if it were hardly there. In the collapsing core, huge numbers of them are created, and for a brief time many begin to interact with the dense material around them. But before that trapped stage fully matters, their production still signals a profound change. The core is converting protons and electrons into neutrons. Ordinary atomic structure is beginning to disappear. The matter that once made plasma, nuclei, and free electrons is being forced toward a more compact identity. In a calmer setting, atoms are mostly empty space, with a small nucleus surrounded by a wide region where electrons exist. In the core of the dying star, that architecture has no room left to survive. The distinction between nuclear matter and the space around it narrows until the idea of ordinary atoms no longer applies. This is why iron core collapse feels so abrupt, even though the star's earlier life was long. The final instability is not a slow exhaustion visible at the surface. It is a threshold crossed inside the hidden center. Once electron pressure fails and electron captures accelerate, the core does not shrink politely. It falls inward. Regions that were once the size of a planet move towards sizes associated with cities. The collapse reaches speeds that make familiar physical intuition unreliable, because matter is no longer drifting under gravity. It is plunging under a force that has lost its main opposition. The timescale is measured in fractions of a second. A star can spend millions of years maintaining balance, then lose the support of its inner core in less time than a human heartbeat. Nothing about the star's long life makes the final moment gentle. The silence of iron is not a pause, it is the removal of the last useful answer. As the core contracts, density climbs toward nuclear values. The nuclei and particles inside are pressed so tightly that the distance between them becomes comparable to the distances inside atomic nuclei themselves. This is a radical change in the meaning of matter on Earth. The solidity of material is mostly the result of electromagnetic forces and the quantum behavior of electrons. Surfaces resist one another because electron clouds do not pass easily through electron clouds. In the collapsing core, those familiar sources of structure are overwhelmed. Electrons are no longer simply arranging matter into atoms. Many are being absorbed into protons. Nuclei are no longer separated by comfortable empty space. The core is being prepared for a state where neutrons become the dominant form of matter, not as isolated particles, but as an enormous compressed body. The iron core does not become a neutron star because iron is special in the sense of being exotic. It becomes one because iron is ordinary nuclear stability taken to its final astrophysical consequence. It is the stable ash of fusion, and that stability deprives the star of a path forward. There is a restraint in that fact that makes the event more unsettling. The catastrophe is not caused by a strange ingredient introduced from outside. It is caused by the successful completion of the star's own nuclear work. The core burns its way to a form of matter that cannot help it burn further, and gravity then turns that success into collapse. The same processes that allowed the star to shine have assembled the condition that ends its life. At this stage, the future divides sharply. If the remaining core were much less massive, a white dwarf might be the final state, held up by electron pressure after the outer layers drifted away. If the collapsed remnant becomes too massive, even neutron pressure cannot prevent further collapse into a black hole. But in the narrow and violent middle, the failing iron core is moving toward a neutron star. That outcome is not guaranteed by beauty or by symmetry. It depends on mass, pressure, the details of the explosion, and the behavior of dense matter under conditions that laboratories cannot truly reproduce. The core is crossing from one regime of physics into another, from fusion-supported plasma to a compact object, where nuclear forces and quantum pressure will decide whether anything remains visible at all. The iron at the centre has done its final work by refusing to do more. It has ended the star's long argument with gravity and opened a much harsher one, in which matter itself must resist collapse without the help of ordinary fusion. What follows is the moment when that inward fall reaches its deepest compression, when electrons and protons are forced together in enormous numbers, and when the centre of a star begins to take on the density of an atomic nucleus stretched across the scale of a city. The collapse into neutrons begins where ordinary matter has already lost its easiest defences. Inside the failing iron core, gravity is no longer merely pressing a hot plasma into a smaller volume. It is forcing particles into arrangements that would never exist under gentle conditions. Electrons, which once moved through the star as part of the pressure holding the core apart, are driven into protons with enough violence that the two become neutrons and release neutrinos. This is not chemistry. And it is not fusion in the familiar sense. It is the undoing of atomic structure under a weight so great that the usual separation between particles can no longer be maintained. A core that had once been comparable to a planet in scale begins to contract toward the size of a city, and during that fall the star crosses from the world of nuclei and electrons into a world where neutrons dominate almost everything that remains. The change is severe because atoms are mostly open space. Even dense metal on Earth is sparse when measured against nuclear matter, with nuclei separated by electron clouds that give material its shape and resistance. In the collapsing core, that spacious architecture is erased. The electrons are not merely squeezed closer to nuclei, many are consumed by protons. The nuclei themselves are forced so near together that the matter approaches the density found inside atomic nuclei. Except now the scale is no longer microscopic, it is macroscopic, stellar, and catastrophic. The result is sometimes described as a giant atomic nucleus, but even that phrase is only a rough doorway into the idea. A neutron star is not an ordinary nucleus enlarged into space. It is a compact object governed by gravity, nuclear forces, quantum pressure, and a density so high that matter has almost no room left to resemble its former self. During the inward plunge, the core falls at an enormous fraction of the speed of light. The motion is not uniform and simple, because the material is layered, turbulent, and changing as it collapses. Yet the direction of the process is unmistakable. The inner regions accelerate inward until they reach densities where the strong nuclear force and neutron degeneracy pressure begin to matter decisively. Neutron degeneracy pressure comes from the quantum rule that certain particles cannot all occupy the same state. Like electrons in a white dwarf, neutrons resist being compressed into identical arrangements. But the scale of this resistance is far more extreme, because it appears only after matter has been crushed almost to nuclear density. It is not a cushion waiting gently beneath the core. It is a last and very hard boundary reached only after most ordinary structure has been destroyed. When the inner core reaches that boundary, it stiffens. The collapse of that central portion slows abruptly, and the material above it continues rushing inward. This sudden change is often described as a bounce, though the word can make the event sound too simple, as if the core were an elastic ball. What happens is stranger. The inner region has become so dense that it resists further compression sharply, while the outer infalling layers crash into it. A pressure wave forms and begins to move outward. At the same time, neutrinos flood the region, carrying energy and information from the transforming core. For a brief span, the centre of the star is neither the old iron core nor yet the calm remnant that might later cool in darkness. It is a newly born compact object, still buried inside the star that is falling onto it. The conversion into neutron-rich matter is not perfectly clean. Some protons remain, some electrons remain. The newborn object is hot, lepton-rich, and filled with trapped particles that will gradually leak away. But its identity has changed. It is now supported mainly by the behavior of dense nuclear matter rather than by fusion. The balance that once held the star open has been replaced by a much harsher resistance, one that exists only because matter has been squeezed to the edge of what can remain a star instead of becoming a black hole. The densities involved are so high that a small change in mass can decide the final fate. If the remnant is not too heavy, neutron pressure and nuclear interactions can halt further collapse. If too much mass remains, the object may continue inward past any stable neutron star state and disappear behind an event horizon. The difference is not a matter of appearance from outside. It is a matter of whether dense matter can find any stable configuration under the burden left behind. This uncertainty gives the moment its quiet tension. The formation of neutrons is not simply a dramatic transformation. It is a trial of matter under gravity. The core has entered a regime where physics known from particles and nuclei must operate inside an object larger than a city and heavier than the sun. Laboratory experiments can probe nuclear matter in fragments and collisions, and theory can describe many possible behaviors, but no human instrument can make a stable piece of neutron star matter on Earth. The star performs the experiment once, violently, and the universe keeps the result in the form of a compact remnant. Even the neutrinos carry part of the story in a way that ordinary light cannot. Photons from the deep core cannot escape quickly through the surrounding star, but neutrinos can move through matter far more freely. During core collapse, they are produced in staggering numbers. At the highest densities, even neutrinos are temporarily trapped, scattering through material that has become thick to almost everything. As the remnant cools, they diffuse outward and remove energy from the newborn neutron star. This neutrino release is one of the main ways the core settles after its first violent formation. It also shows how extreme the conditions have become. Particles famous for passing through planets can be delayed by the density of a stellar corpse in its first seconds of life. Beneath all of this is a change in scale that remains difficult to hold together. The mass involved is stellar, yet the size is closer to that of a city. The original iron core may have been thousands of kilometers across before collapse, but the neutron-rich remnant contracts toward a radius of only about a dozen kilometers. The material does not become dense because it is made of an exotic substance added from somewhere else. It becomes dense because almost all ordinary spacing has been removed. That distinction matters. A neutron star is not magical matter. It is familiar matter driven into an unfamiliar state by a gravitational emergency. Protons, neutrons, electrons, and neutrinos are not strange names from outside the universe. They are part of the same particle inventory that underlies everyday reality. What changes is the pressure, the density, and the fact that gravity has forced them into a configuration where everyday reality has no useful comparison. The birth of the neutron star is therefore both a collapse and a sorting. Gravity strips away the star's previous forms of support, and whatever survives must be able to resist compression at nuclear density. The remnant that emerges is not simply the old core made smaller. It is a different physical object, one whose surface, crust, magnetic field, and later behavior all follow from this first impossible squeeze. Its future as a pulsar, a magnetar, or a quiet cooling remnant depends on spin, magnetic field, mass, and surroundings. But its deepest identity is established here. At the moment when electrons and protons are driven together and the core becomes neutron-rich, the star's long life ends with the destruction of its own atomic openness. The spaces that made matter ordinary are removed, and the remaining particles are crowded into one of the most compact visible forms nature permits. From this compression, the supernova will soon be driven outward, the outer star will be torn away, and the newborn remnant will be exposed. But before the explosion becomes visible, before the shock crosses the star and light announces the death to space around it, the essential transformation has already happened in darkness. A star's center has been crushed into neutrons, and matter has found a final resistance at the edge of collapse. The rebound that follows core collapse is not a simple reversal of motion. Deep inside the dying star, the newly stiffened inner core has halted first, while the outer core and the surrounding layers are still falling inward with enormous speed. The material above does not know, in any gentle way, that the center has changed its condition. It keeps plunging until it strikes the compressed region below, and that collision launches a shock wave outward through the infalling star. For a moment, the star contains two opposite motions at once. Matter is still rushing toward the center, pulled by gravity and by the loss of pressure, while a wave of compression is trying to move outward and unmake the collapse. The future of the star depends on whether that outward motion can survive long enough to reach the outer layers. If it fails, the remnant may keep gaining mass and fall farther inward. If it succeeds, the star is torn apart, and the neutron star is left behind as the dense inner survivor of a much larger body. The word rebound can make the event sound tidy, as though the core simply hits a floor and sends the rest of the star away. In reality, the first shock wave loses strength almost immediately. As it travels outward, it has to push through material that is still falling inward. It also spends energy breaking apart heavy nuclei, reversing some of the nuclear assembly that helped build the iron core. The wave is born violent, but it is not automatically victorious. For a core collapse supernova, one of the central difficulties is explaining how the stalled shock becomes strong enough to explode the star. The answer involves the newborn neutron star, the trapped heat around it, the flood of neutrinos escaping from the dense core, and the turbulent motion of matter in the region just above the remnant. The explosion is therefore not only a bounce, it is an argument between falling mass, escaping energy, and the complicated transfer of momentum through matter under extreme conditions. Neutrinos become especially important because they carry away most of the energy released during the core's formation. They are nearly ghost-like in ordinary matter, but in the dense region near the newborn neutron star, their numbers are so large and the material is so compressed that some of their energy can be deposited behind the stalled shock. This heating does not resemble a flame moving through fuel. It is a subtle but powerful exchange in which particles that usually pass through matter help revive the outward blast. Turbulence can assist by keeping material in the heating region longer, giving the neutrinos more time to act. Convection, rotation, magnetic fields, and instabilities all help shape the outcome. The explosion that eventually appears bright and outwardly clear may have begun as a messy, uneven struggle near the core, where no ordinary surface and no ordinary fire existed. As the shock revives and moves outward, the rest of the star is forced into a final rearrangement. Layers that were once stacked by nuclear burning are lifted, heated, mixed, and expelled. The outer envelope, which may have swollen to immense size during the star's final stages, is driven away into space. The material does not leave quietly. It expands at thousands of kilometers per second, carrying oxygen, carbon, silicon, calcium, iron group elements, and newly made radioactive isotopes into the surrounding galaxy. Some of that material was forged during the star's long life. Some is produced during the explosion itself. The supernova is not only the death of the star, it is also a release of its internal history. Elements that were once hidden in shells and core regions become part of a spreading remnant, available to future clouds, future stars, and future planets. The light of the supernova comes from this expanding debris and from the energy deposited in it. In the first moments, the shock heats the outer layers until they become luminous. Later, radioactive decay helps keep the debris glowing, as unstable nuclei change into more stable forms. From far away, the event can outshine entire galaxies, not because the remnant at the centre is large, but because the star has converted collapse into an enormous outward display. The brightness is the visible announcement of something that began invisibly in the core. The photons that eventually escape tell only the outer part of the story. Long before the supernova becomes a beacon, neutrinos have carried away the deepest energy, and the neutron star has already been born under the falling star. This order matters. The explosion is not what makes the core dense. The core becomes dense first, and the explosion exposes what the collapse has already made. Yet the explosion also decides what kind of compact object remains. If too much material falls back after the shock, the newborn neutron star may be pushed beyond stability and collapse into a black hole. If the explosion removes enough of the surrounding star, the remnant survives as a neutron star, cooling through neutrino emission and settling into a smaller, denser state. Some supernovae may be strong and asymmetric, kicking the neutron star away from its birthplace at high speed. Others may be weaker or fail to produce a clear visible blast. There is no single perfect supernova pattern. The same basic crisis, the collapse of an iron core, can lead to different endings depending on mass, rotation, composition, magnetic fields, and the details of the energy flow near the center. The newborn neutron star does not necessarily sit calmly at the middle of the debris. The explosion can be uneven, and that unevenness can give the remnant a kick. Many neutron stars move through space at extraordinary speeds, carrying the memory of asymmetry in their birth. The blast can also leave behind a nebula, a widening cloud where shocked gas, magnetic fields, and fast particles continue to glow for thousands of years. In some remnants, a pulsar sits inside the expanding material, feeding energy into it and shaping it from within. The supernova is therefore not only a moment, it is the beginning of a long aftermath in which the compact remnant and the ejected layers remain connected by motion, radiation, and history. What was once one star becomes two very different records, a diffuse cloud expanding outward and a dense object cooling inward. This division is one of the most striking consequences of the rebound. A star that once maintained itself as a single, gravitational body is separated into extremes. Most of its visible mass may be scattered into space, thinning as it expands, while a smaller central remnant contains a mass comparable to the Sun within only a few tens of kilometers. The outer debris becomes broad, filamented, and gradually mixed into the interstellar medium. The inner survivor becomes compact, hot, and almost unimaginably dense. The same collapse produces both expansion and compression. It sends matter outward across light years while leaving matter at the center, packed near nuclear density. The supernova is not merely an explosion in the everyday sense. It is a physical sorting of the star into what can escape and what cannot. Seen in this way, the shock wave is the boundary between two destinies. Above it, layers are accelerated outward and become part of the galaxy's chemical inventory. Beneath it, the neutron star remains bound by gravity so strong that its own surface is a place of warped light and brutal pressure. The outer star may spend centuries or millennia spreading into a remnant that telescopes can map, but the central object has already entered a deeper timescale of cooling, spinning, and magnetic decay. The rebound, then, does not erase collapse. It makes collapse visible by throwing the rest of the star away. It reveals the compact result by removing the envelope that once concealed it. From the outside, the supernova may appear as the grand event, the sudden brilliance that marks the star's end. From the inside, it is also a clearing, a violent removal of material from around a core that has crossed into a new kind of existence. The outward blast is enormous, but it is temporary. The debris fades. The shock slows. The light declines. What remains is the object that the explosion could not unmake a neutron star, newly exposed, still intensely hot, still spinning, and carrying within its small radius the compressed consequence of the entire star that came before it. The exposed neutron star is small enough that distance almost hides its meaning. After the supernova debris begins expanding away, the remnant left behind may be only as wide as a city, a sphere with a radius of roughly 12 kilometers, yet it can contain more mass than the Sun. The mind expects a star to occupy space with grandeur, to spread its light across a wide surface, to be large in a way that matches its weight. A neutron star breaks that expectation. Its size belongs to geography. Its mass belongs to astronomy. These two scales are forced into the same object, and the combination makes almost every ordinary comparison fail. A mountain, an ocean, a planet, a metal core. Even a white dwarf can all be dense in familiar ways, but none of them prepare matter for what it means to remove most of the room inside atoms and leave behind a compact remnant held near nuclear density. The star is not merely heavy for its size. It is heavy because its size has been driven down to the last narrow territory where matter can still remain outside a black hole. Density is usually imagined as a property of substances, something that separates wood from stone or lead from water. In a neutron star, density becomes an environment. It determines how gravity behaves, how the surface forms, how light escapes, how particles move, and how the star can exist at all. A fragment the size of a sugar cube. If it could somehow be taken from such a star and held together away from the crushing gravity that made it, would carry a mass comparable to mountains. The comparison is imperfect, because neutron star matter is not a stable material that can be scooped out and placed on a table. It depends on the pressure of the star itself. Without that pressure, the arrangement would not remain ordinary or intact. But the comparison still points toward the central fact. The object contains stellar mass in a volume so small that mass stops feeling like a number and begins to feel like a distortion in the idea of size. On Earth, dense objects are dense because their atoms pack closely, but the atoms still keep their architecture. Nuclei remain tiny centers surrounded by electron structures, and those structures create most of the volume of matter. In a neutron star, that volume has been stripped away. The remnant is not made of atoms in the normal sense through most of its interior. It is made of material compressed until the distinction between one nucleus and the next has lost its familiar meaning. Near the surface, nuclei may still exist in lattice structures, but deeper down the pressure changes them, crowds them, and finally pushes matter into a neutron-rich fluid. The density is therefore not only a measurement, it is a history of collapse preserved in every layer. It records how far gravity has pressed ordinary matter away from ordinary form. This compression also changes the way mass curves space-time around the star. Gravity at the surface is immense, far stronger than anything found on a planet and stronger than the gravity around any normal star. Matter falling onto the surface would strike with devastating energy, because even a small height above the surface exists inside an extreme gravitational well. Escape requires enormous speed. Light itself has to climb out through curved space-time, losing energy as it travels outward. The star is visible only because it is not quite compact enough to trap all light behind an event horizon. That nearness to invisibility gives the neutron star its unsettling place among cosmic objects. It is not a black hole, but it stands close to the boundary. Add enough mass or compress it a little further, and the distinction could fail. The density also means that the surface is not gentle in any normal sense. The gravity pulls material into an almost perfect sphere. smoothing large irregularities far more efficiently than gravity can smooth a planet. Mountains, if they exist, may be only centimeters high. Yet under these conditions, even such tiny elevations can contain enormous mass. The star's shape is controlled by the severity of its own gravity. Features that would be insignificant on Earth become physically costly because lifting matter even slightly above the surface requires extreme energy. The surface may be hot, hard, magnetized, and layered, but it cannot support ordinary landscapes. Its scale of relief is compressed along with everything else. On a neutron star, the word mountain becomes less a measure of height than a measure of resistance against gravity. Temperature adds another layer to the extremity. A newly born neutron star can be incredibly hot, with surface temperatures reaching far beyond those of ordinary stars, though it cools over time. Heat there does not make the object expand into something gentle or diffuse. The gravity is too strong, and the matter too compact. Thermal energy escapes gradually, first through neutrinos from the interior and later through radiation from the surface. The star can glow in X-rays, pulses, and high-energy emission depending on its magnetic field, age, and surroundings. Yet even when it cools, the density remains. Temperature changes the remnant's visible behavior, but not the central fact that a stellar core has been reduced to a body whose physical proportions are almost beyond comparison. The small radius makes its rotation more startling. When the original core collapses, angular momentum is conserved, much as a spinning body turns faster when its mass is drawn inward. A star that rotated modestly before collapse can leave behind a remnant spinning many times each second. In some cases, old neutron stars in binary systems can be spun up even faster by matter falling from a companion, becoming millisecond pulsars that rotate hundreds of times per second. Such speeds would tear ordinary objects apart. A neutron star survives them because its gravity and internal forces bind it with enormous strength. Its density allows it to behave like a flywheel made from collapsed stellar matter, but one whose surface is not a mechanical rim, and whose interior may be fluid, superconducting, or stranger than any solid known on Earth. This combination of compactness and rotation turns the remnant into one of the most precise natural clocks in the universe when its beams sweep past Earth regularly. Still, the clock-like behavior should not obscure the violence of the object. The pulses can be regular because the star is compact, stable, and strongly bound, not because it is mild. Its density gives it endurance. Its gravity forces coherence. Its magnetic field, rotation, and surface emission then translate the coherence into signals that can cross interstellar space. To measure such pulses is to detect the rhythm of matter compressed to a state that would destroy almost anything else. The object seems small in the sky because it is small in space. But its physical authority comes from how much mass has been forced into that smallness. In that sense, a neutron star is a refusal of scale as ordinary experience understands it. The density also shapes the limit of what neutron stars can be. There is a maximum mass beyond which no known pressure can hold the object up against gravity, although the exact value depends on the still uncertain behavior of dense nuclear matter. Observed neutron stars with masses around 2 times that of the Sun show that matter can support extraordinary loads. But the line between a heavy neutron star and a light black hole remains one of the crucial questions in compact object physics. The density of each neutron star is therefore not just a fact about that one remnant. It is evidence in a larger problem. How stiff is nuclear matter when compressed past the densities of atomic nuclei? How much pressure can it generate? What happens at the core when gravity asks more than neutrons can answer? These questions sit inside every mass and radius measurement, because the size of the star reveals something about the hidden material law that supports it. The remnant left after the supernova is therefore more than a compressed ball of neutrons. It is a boundary object, small enough to make a city seem like an appropriate comparison, massive enough to curve space-time with stellar force, and dense enough to turn everyday matter into a misleading guide. Its existence shows that collapse can stop before darkness, but only barely, and only under conditions where the ordinary structure of atoms has already been sacrificed. The next layer of strangeness begins at the surface, where the same density that makes the star so compact also bends light, intensifies gravity, and turns the act of seeing into a lesson in curved space-time. Near the surface of a neutron star, gravity stops being only an invisible pull and becomes the dominant condition of place. The surface is not far from the centre by planetary standards, yet it sits above a mass greater than the Sun, compressed into a radius of only a few dozen kilometres. That closeness matters on Earth. Gravity feels steady because the planet is large, diffuse compared with a neutron star, and mild enough for height, motion, and weight to keep familiar meanings. Around a neutron star, the same ideas are distorted. A small change in altitude can involve a severe change in gravitational energy. Falling material does not merely land, it is accelerated into the surface with enough force to release radiation in X-rays and gamma rays. The star's gravity is not the strongest possible, because a black hole lies beyond it, but among visible solid-surfaced objects it stands near the limit. Matter can still strike a surface. Light can still escape. The object can still be seen, yet everything that escapes does so from the edge of a deep well in space-time. That well changes even the path of light. In ordinary conditions, light travels in straight lines unless it crosses a boundary, passes through a medium, or moves through a gravitational field strong enough to matter. Near a neutron star, gravity is strong enough to bend light dramatically. Photons leaving the surface do not simply fly outward from the patch where they were emitted. Their paths curve through the warped space-time around the star, allowing regions that would normally be hidden beyond the limb to become visible. The result is not a simple view of a round ball with one clean near side and one concealed far side. Depending on the star's compactness, an observer far away may receive light from more than half the surface at once. The front remains visible, but parts of the back can be folded into view by gravity itself. The star does not need a mirror. Its mass bends the routes by which light reaches space. This gravitational lensing turns the surface into a strange optical problem. Hotspots near the magnetic poles may sweep around as the star rotates, and their brightness rises and falls as beams and thermal emission come into and out of view. But because light is bent, the pulses are softened and reshaped. A spot that should disappear cleanly behind the edge may remain partly visible. A surface that should rotate out of sight may leave a lingering signal. The pattern of brightness therefore carries information about the star's mass and radius, because the stronger the curvature, the more of the surface is visible at once. Astronomers can use these changes in pulse shape, together with X-ray observations, to constrain how compact the star must be. The visible surface becomes a measurement tool for the invisible interior. The bend in light is not just spectacle. It is evidence of how tightly mass has been packed. Gravity also stretches the wavelength of escaping light. A photon that leaves the surface must climb away from the neutron star's gravitational field, and in doing so, it loses energy. Its wavelength becomes longer, a change known as gravitational redshift. The same idea applies in weaker form near many massive bodies, but around a neutron star the effect can be substantial. Light born as higher energy radiation at the surface may be observed at lower energy farther away. This does not mean the light tires in an ordinary mechanical sense. It means that space-time itself sets the energy cost of escape. The surface is so deep in the gravitational field that radiation carries the mark of where it began. In principle, Measuring such shifts can help reveal the compactness of the star, though the details are difficult because the surface, atmosphere, magnetic field, and emission processes are all complex. Even when the star shines, it does not give up its measurements easily. The gravity at the surface gives weight an almost unreal meaning. A person or spacecraft could not stand there, not only because of temperature and radiation, but because the force across any extended object would be catastrophic. The side closer to the surface would be pulled much harder than the side farther away, creating tidal stresses that tear matter apart before any ordinary landing could occur. Material falling from a companion star in a binary system may be ripped, heated, and guided by magnetic fields before it reaches the surface. When it finally strikes, the impact can release an enormous amount of energy, far more per unit mass than chemical burning, and even more efficiently than ordinary nuclear reactions in many contexts. Accretion onto a neutron star is therefore one of the ways such remnants become bright after their birth, especially in X-ray binary systems where a companion feeds them. The surface can also behave like the stage for sudden thermonuclear flashes. If hydrogen or helium from a companion accumulates on the neutron star, it may be compressed and heated until unstable nuclear burning ignites across the surface. These X-ray bursts are not the same as the supernova that created the neutron star. They are smaller events in absolute terms, but they are still immense, made possible by the compact object's gravity and the fresh fuel falling onto it. The fuel forms a thin layer, compressed under conditions unlike anything on a normal star. When ignition spreads, the surface can brighten rapidly, then fade as the fuel is consumed and the layer cools. In this way, the neutron star can continue to turn gravity into light long after the massive star that formed it has vanished. Its surface is not passive. It is a boundary where falling matter, nuclear burning, radiation, and magnetic fields can all meet under severe compression. Heat is another part of that boundary. A young neutron star is born at extraordinary temperature, and although it cools rapidly at first through neutrino emission, its surface can remain far hotter than ordinary stellar surfaces for long periods. The heat does not make the object broad or swollen, because gravity holds the star tightly. Instead, the surface radiates from a compact area, often in X-rays, carrying clues about cooling, composition, magnetic fields, and interior physics. A thin atmosphere, perhaps only centimeters or less in scale, can still change the escaping radiation. Hydrogen, helium, carbon, or heavier elements each shape the spectrum differently. Strong magnetic fields can alter how particles move and how photons escape. Thus, even the outermost visible layers are not simple. They are shallow in thickness but deep in consequence, because every photon that leaves them has been filtered through temperature, gravity, and magnetic structure. The surface itself is likely not smooth in the way a polished sphere is smooth, though the gravity allows only tiny departures from roundness. A neutron star crust can support stresses, and magnetic fields may deform it slightly. The highest mountains are not tall by human standards, yet their mass can be enormous because the material is so dense. These deformations matter because a rotating neutron star with an uneven mass distribution can emit gravitational waves, faint ripples in space-time, though detecting such signals from isolated mountains remains extremely challenging. Again, the scale is inverted. A height that would be trivial on Earth can become astrophysically meaningful because it sits on a body of nuclear density spinning under intense gravity. The surface keeps reminding physics that small distances are not always small consequences. The light bending, redshift, tidal forces, heat, and surface gravity all point to the same deeper fact. A neutron star remains visible, but it is visible from the threshold of collapse. It has a surface, but that surface lies in a gravitational field so strong that it changes the route and energy of radiation. It has a shape, but the shape is enforced by gravity powerful enough to flatten almost every ordinary irregularity. It can radiate heat, flare through accreted fuel, and pulse as hot regions rotate into view. Yet none of these behaviors can be separated from the compactness of the object itself. The surface is not merely the outside of the neutron star. It is the place where the hidden density of the interior becomes observable through warped light, violent impacts, and radiation forced to climb out of curved space-time. From there, the next question moves inward again, because beneath the heat and the bent paths of photons lies a crust unlike any planetary crust, a solid layer of iron-rich matter pressed into forms that only extreme gravity can hold together. The outer crust of a neutron star begins where the surface stops being only a source of light and becomes a kind of solid record. Above it, radiation escapes, magnetic fields guide charged particles, and any thin atmosphere is held down with a severity that makes ordinary atmospheres seem almost weightless. Beneath it, the material has already been pressed into a solid layer that owes its existence to the same gravity that crushed the stellar core. This crust is not a crust in the planetary sense, not a cool shell floating over a mantle, not a fractured skin shaped by weather, erosion, or plate motion. It is a rigid arrangement of nuclei and electrons under a pressure so high that even familiar elements become unfamiliar. Near the top, iron group nuclei left by the supernova and shaped by later settling can form a lattice, a repeating crystal structure immersed in a sea of electrons. The nuclei remain distinct, but they do not sit in ordinary chemical bonds. Chemistry has almost no room to matter here. The forces that organize the crust are gravity, electromagnetism, nuclear stability, and the quantum behavior of particles crowded far beyond terrestrial conditions. Iron appears at the outer crust for a reason that reaches back to the star's death. Iron group nuclei are among the most tightly bound forms of ordinary nuclear matter, and under the cooler, lower pressure conditions near the surface they can be favoured as stable residues. But stability in this setting does not mean gentleness. The iron nuclei are stripped of their normal electrons. They exist as bare or nearly bare nuclei embedded in a degenerate electron gas, where the electrons are free to move through the lattice rather than orbiting individual atoms in the familiar way. The solid is therefore metallic only in a highly extreme sense. It conducts heat and electricity well, but it is not metal as it exists on Earth. It is matter after the usual boundaries of atomic life have been removed, leaving nuclei packed into order by pressure and threaded by electrons whose motion is governed by quantum rules. Going deeper, the weight above increases rapidly. Each layer bears the burden of everything above it, and because the surface gravity is so intense, pressure grows over very short distances. The nuclei are forced closer together. The electrons become more energetic. Under these conditions, electrons can be captured by protons inside nuclei, turning them into neutrons and making the nuclei more neutron-rich. This changes the composition with depth. The crust is not one uniform sheet of iron. It is a stratified solid, with different nuclei favoured at different pressures, each layer shaped by the balance between nuclear binding, electron energy, and gravity. The deeper the material lies, the more it has been edited by compression. Matter is not simply squeezed, its internal identity is revised. The outer crust may be only a thin portion of the whole neutron star, perhaps about a kilometre in broad scale depending on the star, but thinness is misleading. A kilometre on a neutron star contains a pressure range that has no close everyday counterpart. The crystal lattice there can be extraordinarily strong. Its strength comes from the dense packing of charged nuclei and the enormous pressure holding the structure together. Breaking it is not like cracking stone. The energy required can be immense, and the consequences can be astrophysical. Stresses may accumulate as the star spins down, cools, or adjusts its magnetic field. When the crust yields, it can fracture or shift in what is often called a starquake. Such events may help explain sudden changes in rotation known as glitches, especially in pulsars, and they may be connected to burst from magnetars when magnetic stress twists and strains the solid layer. The crust is thus not merely a passive shell. It can store tension, it can fail, it can communicate the hidden motion of the star's interior to the outside universe. The relation between crust and interior is especially important because the neutron star is not fully solid. Beneath the crust, and in some regions within it, matter may behave as a superfluid, a quantum fluid that can move with almost no internal friction. Neutrons in the inner crust can flow through the lattice once they drip out of nuclei at higher densities. Even before that deeper transition, the crust's rigidity must be understood as part of a larger coupled system. The solid layer anchors magnetic fields. It interacts with fluids below. It rotates with the star, but not always with perfect simplicity. In a pulsar, the crust can act like the visible clock face, carrying the magnetic field in the emitting regions that sweep beams through space, while superfluid components inside may rotate slightly differently. When angular momentum is transferred between them, the pulse rate can jump. A tiny irregularity in timing can therefore reveal that the neutron star is not a simple sphere, but a layered compact body with solid and fluid parts exchanging stress and motion. This makes the crust one of the most important observable boundaries in the star. The core may hold the deepest mystery, but the crust often translates that mystery into measurable behavior. It affects thermal emission because heat from the interior must pass through it before reaching the surface. It affects magnetic evolution because electrical currents in and around the crust can support or rearrange magnetic fields. It affects burst activity because sudden failures in the crust can release or redirect energy. Its composition affects the spectrum of escaping light and the cooling pattern of the star. A layer that is small compared with the star's radius can still decide what kind of signal reaches telescopes. In that sense, the crust is less like a decorative shell and more like a narrow instrument through which the buried physics becomes audible. The hardness of this layer also changes the meaning of landscape. On Earth, mountains rise because rock resists gravity and tectonic forces build relief. On a neutron star, gravity allows only very low elevations, but the crust's density and strength make even tiny irregularities significant. A deformation only centimeters high can represent an enormous amount of mass. If the star spins, such an asymmetry may create a changing gravitational field and could, in principle, emit continuous gravitational waves. The challenge is that neutron star mountains are expected to be small, and space-time is difficult to disturb measurably from across the galaxy. Yet the idea itself reveals the strange compression of scale. A surface feature too low to notice in a room can matter when it belongs to an object heavier than the Sun and spinning many times each second. The crust forces familiar words to shrink and grow at the same time. Mountain becomes almost flat in height, yet vast in mass. Solid becomes not ordinary hardness, but nuclear pressure rigidity. Beneath the outer iron-rich layers, the approach to the inner crust brings matter toward a threshold called neutron drip. At this point, nuclei become so neutron-rich that some neutrons can no longer remain bound inside them. They begin to form a free neutron fluid around the lattice. This transition marks a deeper alteration in the crust's identity. The material is no longer simply a solid of nuclei and electrons. It becomes a mixture of lattice and free neutrons. with quantum fluids sharing space with ordered nuclear structures. The crust, which began near the surface as something that could still be loosely compared to an exotic metal, moves downward into matter with no ordinary analogy at all. It is still outside the core, yet already it has left the idea of atoms far behind. The iron crust therefore serves as a threshold between visibility and the deeper unknown. It is the layer where the neutron star still has something like a surface, something like solidity, and something like composition by nuclei. But every one of those familiar terms has been forced into a more extreme meaning. It carries traces of the supernova, bears the stress of magnetic fields, regulates heat, anchors pulses, and records the slow adjustment of a compact star that is cooling and spinning through time. The deeper the crust goes, the less matter can preserve the shapes that once made it recognizable. The nuclei become heavier with neutrons. The electrons become more energetic, and the lattice approaches a region where even nuclei begin to deform. What begins as an iron-rich skin under impossible weight becomes a passage into a stranger arrangement, where nuclear matter stretches into rods, sheets, and tangled forms that make the next layer of the star seem almost biological in name, though it is born entirely from pressure. At the base of the crust, the neutron star begins to abandon even the last familiar shapes of nuclei. The outer crust could still be described, with caution, as a lattice of compact nuclei surrounded by electrons. Deeper down, free neutrons already move through that lattice, making the inner crust stranger than any metal or rock. But as pressure increases toward the boundary with the core, the nuclei are forced so close together that their individuality becomes unstable. They do not simply remain as round droplets packed more tightly. The competition between nuclear attraction, electrical repulsion, neutron pressure, and geometry reshapes them. Matter searches for arrangements that cost the least energy under a burden almost beyond comparison. The result is nuclear pasta, a name that sounds gentle only because the physics beneath it is difficult to name in ordinary terms. In this region, nuclei may stretch into rods, flatten into sheets, connect into tubes, or form more tangled structures, not because they are soft in any normal sense, but because the pressure leaves them few other ways to exist. The image of pasta is useful only as a first approximation. It gives the mind a set of shapes, strands, slabs, tunnels, and layers. But there is no cooking, no softness, no separate material suspended in a source. These are nuclear structures, made from protons and neutrons, embedded in a sea of electrons and free neutrons, compressed by the gravity of an object heavier than the sun. The rods, sometimes called spaghetti, and the sheets, sometimes called lasagna, are not metaphors for texture. They are attempts to describe how nuclear matter may minimize energy when round nuclei are no longer the best arrangement. At lower density, a sphere gives a nucleus an efficient shape, keeping particles bound while reducing surface energy. At higher density, the available space changes. The spheres crowd together. Their surfaces press close. New shapes become favourable because the material is moving toward uniform nuclear matter, but has not reached it yet. The pasta layer is therefore a transition zone, a place where the crust stops behaving like a lattice of distinct nuclei and begins to resemble the dense fluid of the core. What makes nuclear pasta especially important is that it may be extraordinarily strong. Some calculations suggest that it could be among the strongest materials in the universe, able to withstand stresses far beyond any solid on Earth. Its strength comes from the way nuclear forces bind its structures and from the immense pressure surrounding them. Yet strength here does not mean a rigid object in the everyday sense. The pasta may be elastic, tangled, layered, defective, and mixed with fluids in ways that make its behavior hard to reduce to one simple property. It may resist breaking, but it may also deform, creep, or rearrange under long-term stress. The question is not only whether nuclear pasta exists, the question is how it behaves inside a star that is cooling, spinning, magnetized, and slowly changing over thousands or millions of years. In the calm language of physics, this region affects the equation of state, the relation between pressure, density, and composition that decides how a neutron star supports itself. In the quieter language of the object itself, the pasta is part of the hidden architecture that determines how the star bears its own weight. The depth at which pasta forms depends on the star and on the uncertain properties of dense nuclear matter. It lies near the bottom of the crust, where densities approach those inside atomic nuclei. Above it, the inner crust still contains neutron-rich nuclei arranged in a lattice, with free neutrons moving between them. Below it, the core may contain a more uniform neutron-rich fluid. Between those regimes, pasta appears because matter is neither fully separated into nuclei nor fully blended into one continuous phase. It is an in-between state, and in neutron stars, in-between states can be physically decisive. A thin layer by radius can contain enormous mass. A small uncertainty in composition can alter cooling, vibration, magnetic evolution, and the way the crust couples to the core. The pasta may be hidden, but it is not irrelevant. It is one of the places where microscopic nuclear physics becomes a macroscopic property of a stellar remnant. One consequence involves heat. A neutron star cools by releasing energy from its interior, first mainly through neutrinos and later through radiation from the surface. Heat must pass through the crust, and the pasta layer may conduct heat differently depending on its structure. If the pasta is ordered in broad sheets or rods, heat may move more easily in some directions than others. If it is tangled and disordered, it may scatter particles more strongly and slow the flow of energy. This matters because observations of cooling neutron stars, especially those in binary systems that are heated by accretion and then allowed to cool, can reveal how efficiently the crust conducts heat. The glow seen from far away is shaped by matter that cannot be seen directly. The surface temperature becomes a delayed message from the deep crust. A nuclear pasta may decide how that message is filtered. Another consequence involves neutrinos. In some models, nuclear pasta may affect the rate at which neutrinos are emitted or scattered in the star's outer interior. That influence is especially important in young neutron stars and in the early seconds after birth, when neutrinos carry away enormous energy. The exact role is still uncertain, because the pasta phase is difficult to simulate and depends sensitively on nuclear interactions. Yet the possibility matters because neutrinos are one of the main cooling channels for dense remnants. A layer that changes neutrino behavior can alter the thermal history of the star. The pasta may also influence rotation. Neutron stars often behave as remarkably stable clocks, but pulsars sometimes glitch, suddenly spinning a little faster before relaxing again. One explanation involves angular momentum stored in superfluid neutrons inside the crust. Those neutrons can form quantized vortices, tiny rotating structures that pin to the crustal lattice or to imperfections, then unpin and transfer angular momentum to the solid crust. Nuclear pasta may change how this pinning works near the base of the crust. Its complex shapes could create strong or unusual anchoring sites, affecting how the superfluid interior couples to the outer crust. This does not mean every glitch is caused only by pasta, but it makes the pasta layer part of the broader timing problem. The regular pulse from a neutron star may carry the trace of hidden nuclear shapes buried far beneath the surface. Magnetic behavior may also depend on this deep crustal region. In magnetars, where magnetic fields are especially intense, stresses can build in the crust and release energy in bursts. The mechanical properties of the crust, including the pasta at its base, affect how those stresses are stored and transmitted. A stronger or more complex pasta layer could influence the way fractures propagate, how the crust yields, and how magnetic energy reaches the surface. This is still an active area of study because magnetars involve the coupling of crust, core, magnetosphere, and magnetic field evolution. But the general point is clear. The pasta is not merely a curiosity of naming. It may help determine how a neutron star cracks, vibrates, cools, and pulses. Its shapes could affect events that become visible across thousands of light years. The strangeness of nuclear pasta is therefore not only in its appearance, it is in the way it joins scales that should feel separate. The same physics that controls the binding of protons and neutrons may influence the timing of a pulsar, the cooling of a young remnant, and the bursting of a magnetar. The structures themselves may be microscopic or mesoscopic by human standards, but they exist throughout a global layer under a star's gravity. Their collective behaviour becomes part of the neutron star's body. This is what makes the lower crust so difficult and so important. It is not deep enough to be the core, where matter may become still more uncertain. But it is already too extreme to belong to the known solid world. It is a boundary where nuclear matter is stretched into shapes that ordinary matter never needs to find. At the bottom of this layer, the last recognizable nuclear structures begin to dissolve into the more uniform matter below. The crust gives way to the core, and the language of rods and sheets becomes less useful. What waits underneath is less certain still. The pasta has already shown that pressure can make matter inventive, bending nuclei into forms that seem almost impossible, only because everyday physics never asks them to exist. But beneath the pasta, even those forms may disappear, leaving a deeper question about whether neutrons remain intact, whether new particles appear, or whether the core hides a phase of matter that no laboratory has ever held steady. Beneath the nuclear pasta, the neutron star enters its most uncertain interior, because the core asks physics to describe matter at pressures that no laboratory can hold in stable form. The crust, for all its strangeness, still offers shapes that can be pictured with some restraint, including nuclei in lattices, free neutrons, rods and sheets of nuclear matter. The core removes even that limited comfort. It is expected to contain an ocean of mostly neutrons, with some protons, electrons, and perhaps heavier particles, all compressed into a fluid so dense that the normal spacing of matter has vanished. Yet the word neutron may itself become incomplete at sufficient depth. A neutron is not indivisible. It is made of quarks bound together by the strong force, and under the central pressure of a massive neutron star. Some theories suggest that the boundaries between individual neutrons could begin to lose meaning. The deepest region may therefore be less like a sea of separate particles and more like a new phase of matter, held between the known behaviour of nuclei and the still unclear behaviour of quarks under gravity. This uncertainty is not a small missing detail. It reaches into the largest measurable properties of the star. The core decides how much pressure the neutron star can generate against its own weight, and that pressure helps determine the relation between mass and radius. A star with a stiffer interior can hold itself at a larger radius for a given mass. A softer interior compresses more tightly. These differences decide where the maximum mass lies, where the neutron star boundary ends, and where black hole collapse begins. Observed neutron stars with masses around twice that of the Sun show that dense matter can be remarkably strong, but they do not reveal exactly what carries that strength. The core could remain dominated by neutrons interacting through nuclear forces. It could allow new particles to appear when the pressure makes them energetically favourable. It could contain matter where quarks move more freely than they do inside ordinary protons and neutrons. Each possibility changes the hidden support structure of the star. The name neutron star may therefore describe the broad outcome while concealing the deepest composition. One candidate for the inner core is a phase containing hyperons, heavier cousins of protons and neutrons that include strange quarks. In ordinary conditions, they are unstable and short-lived. But inside dense matter, they may become possible because the system can lower its energy by converting some particles into new forms. Their appearance would not be decorative. It would soften the matter in many models, reducing pressure support and making it harder for the star to hold up high masses. That creates a tension. If hyperons appear too easily, some theories struggle to explain the heaviest known neutron stars. The particles are plausible, but their consequences are demanding. The core may permit them only under certain interactions, or resist them longer than simple arguments suggest. In this way, even the possible presence of strange matter becomes a question not of fantasy, but of balance sheets written in energy, pressure, and gravity. Another possibility is deconfined quark matter. In ordinary nuclei, quarks are confined inside protons and neutrons, never isolated under normal conditions. At extreme density, however, matter may cross into a state where quarks are no longer tied to individual nucleons in the same way. They may form a dense fluid containing up, down, and perhaps strange quarks, with electrons or other particles maintaining charge balance. This does not mean the core becomes a fireball like those briefly created in particle collisions. A neutron star core is cold compared with its density, old after its birth, and held in equilibrium by gravity. If quark matter exists there, it is a stable or long-lived phase under pressure, not a fleeting spray of particles. It would be one of the few places in the present universe where such matter might persist on astronomical timescales. The difficulty is that quark matter can hide. A neutron star with a quark core may not announce itself with one unmistakable signal. Its mass, radius, cooling behavior, spin evolution, oscillations, and merger waves may all carry clues, but each clue has to be separated from uncertainties in the crust, magnetic field, atmosphere, and history. A smaller radius might hint at softer matter, but it could also depend on other model choices. A sudden change in cooling might suggest enhanced neutrino emission, but the surface layers can complicate the message. A gravitational wave signal from a merger can reveal how easily the stars deform each other, but the interpretation depends on the entire equation of state, not only on the core is therefore not simply hidden by distance. It is hidden by degeneracy, by the fact that different interiors can sometimes produce similar outward behavior. Science advances by narrowing that overlap. The deepest core may also contain superconducting or superfluid states. In dense matter, particles can pair up in ways governed by quantum mechanics, allowing the fluid to move or carry currents with unusual efficiency. Neutrons may form a superfluid. Protons may form a superconductor. If quark matter exists, quarks themselves may pair in even more exotic patterns. These states matter because they affect cooling, magnetic field evolution, rotation, and how the interior responds to stress. A superfluid does not rotate like an ordinary fluid. It carries rotation through quantized vortices, discrete threads of circulation. A superconductor handles magnetic fields in ways that can trap or arrange them into narrow structures. The star may look like a compact sphere from outside, but inside it could contain quantum-ordered fluids moving under gravity with almost no resemblance to water, metal, or plasma as known on Earth. The problem is not a lack of ideas, it is almost the opposite. Dense matter offers several possible pathways, each supported by a different part of theory, observation, and nuclear experiment. But no single pathway has yet forced all the others away. Measurements from pulsars, from hot surface emission, from cooling stars, and from gravitational waves have begun to tighten the allowed range. They show that neutron star matter must be strong enough to support heavy remnants and not so deformable that merging stars would stretch too easily before collision. But between those boundaries, multiple interiors remain viable. The core can be partly known by what it permits the whole star to do, while still remaining unknown in its detailed composition. This is a rare kind of mystery, because it is not empty. It is crowded with constraints, each one making the unknown more precise. The inner core also determines what happens during the most violent endings. When two neutron stars spiral together, their cores are compressed, heated, and torn into a short-lived object that may collapse into a black hole or survive temporarily as a massive remnant. If quark matter or other exotic phases appear only at the highest densities, a merger may create them suddenly, leaving traces in gravitational waves, neutrino emission, or the matter ejected into space. The collision becomes not only an astronomical event, but a natural experiment in nuclear physics. It forces the core into conditions beyond those of an isolated neutron star, and then sends out signals that carry partial records of the response. It writes it in deformability, collapse time, remnant oscillations, and the composition of the debris. Still, those fragments matter, because they may reveal what the quiet interior never shows on its own. For now, the core remains the place where certainty thins but discipline must increase. It is tempting to fill it with the most exotic possibility. To imagine strange quark matter or unknown phases simply because the conditions are extreme. But the more careful path begins with what is required. The core must support the observed mass. It must match the measured radii as well as they are known. It must cool in ways that resemble real neutron stars. It must behave during mergers in ways that fit gravitational wave data. Within those requirements, speculation can enter, but only as a set of possibilities constrained by evidence. The interior may be mostly neutrons, it may contain hyperons, it may hide deconfined quarks, it may pass through several phases with depth, each one appearing only when pressure becomes high enough. The neutron star, already nearly impossible at the surface, becomes still more difficult at the centre, because the question is no longer only how dense matter can be. It is what matter becomes when density removes the boundaries that once made its particles distinct. The crust gave the star structure. The pasta showed matter changing shape. The core asks whether matter changes identity. Until observations become sharper, the answer remains suspended inside the small dark volume at the centre of the remnant, where gravity presses familiar particles towards states that may exist nowhere else in stable form. A neutron star does not become quiet simply because the explosion has ended. Once the outer layers have been thrown into space and the compact remnant is exposed, the star may still be rotating with extraordinary speed, carrying a magnetic field intensified by collapse. The same conservation of angular momentum that makes a shrinking body spin faster turns the newborn remnant into a rapid wheel of dense matter. A core that once rotated as part of a large star has been compressed into a sphere only a few dozen kilometers across, so its rotation can accelerate until a single turn takes only seconds, fractions of a second, or even less. At the same time, magnetic field lines are crowded into the smaller surface area, and internal motions can strengthen them further. The result is not a dead ember in the usual sense. It is a compact engine, hot, magnetized, and spinning, able to send signals across the galaxy long after the bright supernova has faded. This is the setting in which pulsars first become understandable. A pulsar is a neutron star whose emission appears to pulse because its radiation beam sweeps across the line of sight as it rotates. The star does not need to brighten and dim like a lamp being switched on and off. Its rotation does the work. Magnetic poles need not align with the spin axis. So charged particles accelerated along magnetic field lines can produce beams of radio waves, X-rays, or gamma rays that move through space like the sweep of a lighthouse. When Earth lies in the path, telescopes receive a flash with each rotation. The pulse is therefore a geometric effect. a rhythm made from spin, magnetism, and alignment. If the beam never crosses Earth, the same kind of star may remain unseen by that method. A pulsar is also a viewing arrangement between a rotating neutron star and a distant observer. Their pulses could arrive with a regularity rivaling clocks, and that regularity came from the stability of the spinning remnant. Ordinary stars cannot rotate so quickly without tearing themselves apart, and ordinary planets cannot produce such intense magnetospheric emission. A neutron star provided the scale required. It could be small enough to spin rapidly, massive enough to remain bound, and magnetic enough to accelerate particles into beams. Once that connection was made, pulsars became one of the clearest ways neutron stars revealed themselves. The pulse was not merely a signal, it was a signature of compactness. The magnetosphere around a pulsar is not empty space. It is filled with charged particles forced to move under the influence of rapid rotation and powerful magnetic fields. Electric fields can pull particles from the surface or create pairs of electrons and positrons, feeding streams of plasma that follow open field lines away from the star. These particles radiate as they accelerate, and the radiation pattern depends on the geometry of the magnetic field, the energy of the particles, and the regions where emission is produced. Some pulsars shine strongly in radio, others are bright in high-energy bands. Some have complex pulse shapes with multiple peaks, suggesting that the beam is not a simple cone but a structured region of emission. The steadiness of the pulses can coexist with fine detail, because the star's rotation is stable while the magnetosphere remains rich. Over time, pulsars slow down. They lose rotational energy as radiation and particle winds carry energy away. The spin period lengthens gradually, and the rate of slowing can be measured with great precision. From this, astronomers infer properties such as magnetic field strength and characteristic age. Though these estimates carry assumptions and must be used carefully, a young pulsar may still sit inside the supernova remnant that formed it, injecting energy into the surrounding nebula. An older pulsar may move far from its birthplace, crossing the galaxy as a compact clock whose beam happens to sweep past Earth. Some pulsars in binary systems are spun up by accretion from a companion, becoming millisecond pulsars that rotate hundreds of times each second. These recycled pulsars can be astonishingly stable, because the long transfer of matter and angular momentum has smoothed their rotation into a regular state. Pulsars also reveal the interior through small departures from perfect timing. A glitch occurs when the rotation suddenly increases by a tiny amount, followed by gradual recovery. These events suggest that the crust and the superfluid interior are not always rotating in perfect lockstep. Angular momentum can be stored in quantized vortices inside the superfluid, pinned for a time to the crust or to structures in the inner layers, then released when conditions change. The visible effect is a small jump in the pulse rate, but behind it may be a transfer between different components of the star. A regular signal becomes a probe of hidden mechanics. The neutron star is not a rigid ball turning as one simple object. It is a layered body, with crust, superfluid, magnetic field, a magnetosphere coupled imperfectly across time. Magnetars represent a different emphasis in the same family of remnants. They are neutron stars whose magnetic fields are so intense that magnetic energy, rather than rotation alone, dominates much of their visible behavior. Their spin is usually slower than that of many ordinary pulsars, often measured in seconds, but their magnetic fields can reach values far beyond those of typical radio pulsars. In a magnetar, the field is not merely a guide for charged particles. It becomes a reservoir of energy able to stress the crust, twist the surrounding magnetosphere, and power bursts of high-energy radiation. The star may rotate like a pulsar, but its most dramatic activity comes from magnetic decay and rearrangement. The field is strong enough to make the crust part of an electrical and mechanical system under long strain. When magnetic stresses build, the crust may yield or shift. That motion can disturb the magnetosphere, accelerating particles and releasing radiation in sudden flares. Some magnetar bursts are brief, others are far more powerful, including giant flares that release enormous energy in gamma rays and X-rays. The event is not a supernova and does not destroy the star, but it shows that the remnant still carries internal power. The surface can crack, the magnetic field can untwist, and the surrounding plasma can glow before settling again. Magnetars are not mysterious because they are vague. They are mysterious because magnetic fields at that strength turn the entire outer star into a stressed, evolving system. The fields may also alter matter at the surface. In extreme magnetism, atoms and plasma behave differently. Photons propagate through magnetized vacuum in subtle ways, and radiation can be polarized by the field before it leaves the region around the star. These effects make Magnetars laboratories for physics under magnetic conditions far beyond terrestrial production. They also complicate interpretation. A surface temperature, a spectrum, or a pulse profile cannot be read as if the star were an ordinary hot sphere. The magnetic field changes the atmosphere, the radiation pattern, and the flow of heat through the crust. What arrives at a telescope is shaped by rotation, magnetism, gravity, and surface composition together. The signal is rich, but never simple. Pulsars and magnetars therefore show two faces of the same compact inheritance. In one, rotational energy is gradually spent through beams and winds, producing pulses regular enough to map orbits, test gravity, and reveal tiny changes in spin. In the other, magnetic energy dominates, producing bursts, flares, and slow changes that expose the strain of a field embedded in dense matter. Some neutron stars may occupy regions between these categories, and a single object can show behavior that blurs the boundary. The classification is useful, but nature does not always obey labels cleanly. What unites them is the compact remnant beneath the emission, the same crushed core whose density, crust, superfluid interior, and magnetic field make the signals possible. By the time a pulsar beam crosses Earth or a Magnetar flare reaches a detector, the supernova that formed the star may be ancient history. The debris may have faded. The birthplace may have dispersed, and the neutron star may have travelled far through the galaxy. Yet the remnant still communicates through timing and magnetic unrest. Its pulses are not voices, and its bursts are not messages in any intentional sense, but they are records of rotation, field strength, internal coupling, and dense matter under stress. A neutron star can seem like the end of a stellar life, but pulsars and magnetars show that the end remains active. The collapsed core continues to spend its stored motion and magnetic energy into space, and those signals prepare the final widening of the story, where neutron stars no longer act alone but meet one another in pairs, spiral inward, and turn compressed matter into the source of some of the heaviest elements in the universe. A binary neutron star system begins as a quiet-looking arrangement only from far away. Two compact remnants orbit one another in the aftermath of massive stars that have already died, each one carrying a city-scale body, a strong gravitational field, and the compressed memory of a supernova. Their separation may be large enough for the pair to persist for millions or even billions of years, but the orbit is not perfectly permanent. Every circuit sends a small amount of energy away as gravitational waves, ripples in space-time produced by accelerating masses. For ordinary objects, the effect is immeasurably weak. For neutron stars, where more than a solar mass can move through orbit inside a compact system, the loss becomes slow but decisive. The stars do not need to touch at first. They fall inward by radiating away the energy that keeps the orbit wide, and the long spiral begins with no explosion. Only a gradual tightening written into space-time itself. As the orbit shrinks, the motion accelerates. The neutron stars circle faster, drawing closer, sending stronger gravitational waves outward. The waves carry a record of the masses, the orbital speed, and the way each star responds to the other's gravity. Unlike black holes, neutron stars have material surfaces and deformable interiors. As they approach, each star raises tides on the other, not oceans as on a planet, but distortions in dense nuclear matter. The amount of deformation depends on the equation of state, the hidden relation between pressure and density inside the star. A stiffer star resists stretching more. A softer star yields more. Thus, the inspiral is not only a prelude to collision, it is an experiment in dense matter. The gravitational waves do not show the core directly, but they reveal how much the entire star can be pulled out of shape before contact. In the final moments, the orbit becomes too fast for calm comparison. The stars whirl around each other many times per second, and the distance between their surfaces closes. Magnetic fields interact, crusts strain, tidal forces grow severe. The stars may begin shedding material even before full merger, especially if their masses are unequal. Then contact occurs, and the distinction between two bodies is violently erased. Dense matter collides with dense matter at speed set by gravity. Heat rises, shocks form, and the combined remnant is born in a state too massive and too hot to be described as a simple larger neutron star. For a short time, depending on the total mass and the stiffness of the matter, the merger may produce a hypermassive remnant supported by rapid rotation and thermal pressure. If that support fails, it collapses into a black hole. If it survives longer, it becomes a temporary laboratory where neutron-rich matter is driven beyond even the conditions found in isolated stars. The collision also throws material outward. Some of it is torn from the outer layers by tidal forces, some is blown out by shocks, some later escapes from the hot disk that may form around the central remnant or newly born black hole. This expelled matter is crucial because it is extraordinarily rich in neutrons. In ordinary stellar fusion, nuclei build up step by step under high temperature and pressure, but the heaviest elements require a different path. They require environments where nuclei can capture neutrons rapidly, faster than they can decay. This is called the rapid neutron capture process. In the ejector from neutron star mergers, the supply of free neutrons can be so large that seed nuclei are driven far from stability, growing into heavy, neutron-rich forms that later decay into stable elements. Gold, platinum, uranium, and many other heavy nuclei can be made in this way. The merger does not shine because it is merely hot. It shines because new atomic nuclei are being assembled and then decaying, heating the expanding debris from within. This glow is known as a kilonova, a transient event fainter than many supernovae but rich in information. As the radioactive debris expands, its light changes colour and brightness over days. Some material, containing lighter heavy elements, can let bluer light escape earlier. Other material, containing lanthanides, absorbs visible light strongly and re-emits energy in redder and infrared wavelengths. The colour therefore becomes a clue to composition. The light curve becomes a record of how much matter was ejected, how fast it moved, and what kinds of nuclei formed inside it. A kilonova is the visible afterglow of nuclear rearrangement in matter that once belonged to the crusts and outer interiors of neutron stars. It is alchemy under gravitational pressure, followed by the slow release of radioactive heat into space. The merger also produces a burst of gamma rays if conditions align properly. A narrow jet may form near the central remnant or black hole, drilling through surrounding debris and releasing high-energy radiation as it escapes. Whether the jet points toward Earth determines how bright and brief the gamma-ray signal appears. This dependence on angle means that some mergers may produce powerful jets that are hard to see directly, while others may be detected through gravitational waves and kilonova light even when the jet is off-axis. The full event is therefore multi-messenger. Gravitational waves carry the motion of the dense masses. Light carries the heating, composition, and outflow geometry. High-energy radiation carries the behavior of relativistic jets. Each messenger is incomplete alone, but together they turn a collision into a layered physical record. The merger of neutron stars shows that these remnants are not only endpoints of stellar evolution, they are also sources. They seed galaxies with material that ordinary stellar burning cannot easily provide. The iron in planets can come from earlier generations of massive stars and supernovae, but much of the heaviest material may owe its abundance to compact mergers, where neutron-rich matter escapes and decays into stable forms. This does not mean every atom of gold in the universe has one simple origin, because astrophysical histories are mixed and complex. But neutron star mergers are now understood as major factories for rapid neutron capture elements. Their importance comes from the same extremity that made them difficult to imagine. A star collapses into nuclear density matter. That matter later collides with another remnant. Only then, in the second violence, does some of it escape and become chemically ordinary enough to join dust, planets, and eventually tools, circuits, and living bodies. There is a restraint in the timing. The heavy elements are not made when the first massive star burns normally. They are not made simply because the supernova is bright. They require a later union between two compact remnants, often after a long delay while gravitational waves drain the orbit. Two dead stars may travel together through the galaxy for ages before they finally meet. When they do, the event may last only moments in its most intense form, yet the material it releases can remain in galactic circulation for billions of years. The contrast is severe. A brief collision creates atoms that outlast the remnants, drifting into clouds that cool, condense, and form new systems. The merger is sudden, but its chemical consequence is patient. It joins the short timescale of relativistic gravity to the long timescale of galactic recycling. At the center of the merger, the final object depends on mass and support. Often the combined remnant is too heavy to remain a neutron star for long. It collapses into a black hole, leaving a disk of hot material that continues to feed outflows. In some cases, a massive neutron star may survive briefly or perhaps longer, supported by rotation before magnetic braking and gravitational radiation remove that support. This uncertainty matters because the lifetime of the remnant affects the ejector, the jet, and the kilonova signal. A prompt collapse may swallow more matter and produce different emission than a delayed collapse. Once again, the hidden equation of state shapes what the universe sees. The collision therefore becomes another way to ask what neutron star matter is made of, not by opening the star, but by watching what happens when two such stars destroy each other. The aftermath widens until the original bodies are gone as recognizable stars. Gravitational waves pass through space and fade. The kilonova light dims, the debris expands, cools, and mixes into the interstellar medium. Some heavy atoms remain near the remnant. Others travel far, stirred by galactic motion and future star formation. What was once compressed inside neutron-rich matter becomes part of a diffuse chemical inheritance. The objects that seemed most removed from ordinary life become one of the reasons ordinary matter can include rare and heavy elements at all. A neutron star merger is therefore not only an ending written in collapse, it is a release from collapse. A moment when matter locked at nuclear density is thrown back into space and allowed, over immense time, to become part of worlds that no longer remember the violence that made them. A heavy atom does not carry a memory in any conscious sense, but its nucleus preserves a physical history. Gold, platinum, uranium, iodine, and many other elements are not simple products of quiet stellar burning. Some are assembled in rare, violent conditions where neutrons are abundant enough to build nuclei far heavier than iron before decay settles them into more stable forms. Once such atoms leave a neutron star merger, they do not remain marked by the event in a visible way. They become part of expanding debris, then part of a wider galactic mixture, then part of clouds so cold and diffuse that the violence of their origin seems almost disconnected from their later calm. The same matter that once belonged to crushed stellar cores can drift through interstellar space as dust, gas, and microscopic grains, spread by shock waves, stirred by gravity, and diluted into the slow circulation of a galaxy. The return is not immediate. A kilonova releases neutron-rich material at high speed, but space does not quickly organize that material into new worlds. The ejector expands and cools. Radioactive nuclei decay. Some atoms attach to dust grains, some remain as gas. Galactic motion folds the debris into reservoirs of interstellar matter, where it may mingle with material from supernovae, stellar winds, dying red giants, and older generations of star formation. The galaxy becomes a patient mixing chamber, capable over immense time of spreading rare elements far from their birthplace. A neutron star merger may occur in one region, yet its products can later be found in a molecular cloud elsewhere. After orbiting through the galaxy and surviving the long intervals between one star-forming era and the next, when a cold cloud begins to collapse under gravity, that older chemical inheritance becomes part of the next system. Most of the cloud is hydrogen and helium, the ancient light elements that dominate the universe, but mixed through it are heavier atoms made by stars and compact remnants, small in abundance but decisive in consequence: carbon, oxygen, silicon, iron. And the rapid neutron capture elements are present as traces, each one carrying a different origin story. Dust grains help the cloud cool. Cooling allows denser clumps to form. Denser clumps can fragment into stars and disks around a newborn star. Leftover material settles into a rotating protoplanetary disk, and within that disk, solids collide, stick, break, and gather again. The heavy elements from older deaths become minerals, metals, ices, radioactive heat sources, and chemical possibilities. They are no longer part of a remnant. They have become ingredients. A rocky planet cannot be built from hydrogen and helium alone. It requires oxygen to bind with silicon and magnesium into stone. It requires iron and nickel for cores. It requires carbon, nitrogen, phosphorus, sulfur, and many other elements for complex chemistry. Some of these come from massive stars and their supernovae, some from quieter stellar processes, and some from neutron star mergers or similarly neutron-rich environments. The exact inventory of any world is the result of many sources layered through time. No planet is the monument of one death. It is a collection of many endings, many releases, many cycles of collapse, burning, explosion, wind, merger, and condensation. The solar system formed from such a mixture, enriched by earlier generations. Its rocks contain evidence of short-lived radioactive isotopes from nearby stellar events, stable heavy elements from older galactic production, and rare nuclei that could only have been made under extreme neutron-rich conditions. The story then narrows from a galaxy to a disk, from a disk to planetesimals, from planetesimals to planets, and from planets to ordinary materials. Gold becomes a vein in rock, or a grain in sediment, or a trace in seawater. Uranium becomes part of minerals that release heat through radioactive decay, helping shape the thermal evolution of rocky worlds. Platinum group elements become locked in metallic phases, sometimes sinking toward planetary cores, sometimes arriving again through later impacts. Iodine and other heavy elements enter chemical cycles that eventually matter to living systems. The path is never straight. Atoms are buried, melted, erupted, eroded, dissolved, carried, and reassembled. Their cosmic origin does not make them rare in experience because they shine with visible strangeness. It makes them rare because the universe had to arrange extreme conditions before they could exist at all. On Earth, heavy elements become ordinary by being incorporated into familiar forms. A wedding ring does not display the neutron flood that helped build its nuclei. A medical isotope does not carry the shape of the merger debris. A circuit does not reveal the compact star whose matter once escaped into space. Technology depends on elements whose origins are distributed across deep astrophysical time. But the finished object hides that scale beneath usefulness. Gold conducts, platinum catalyzes, uranium releases nuclear energy. Rare heavy elements help shape electronics, medicine, industry, and measurement. The same is true of living matter, though life is not made mostly of the heaviest elements. Biology is built chiefly from lighter elements, especially carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Still, heavier atoms enter life in smaller but meaningful ways through trace elements, environmental chemistry, and planetary geology. More broadly, life depends on a rocky world with a complex chemical inventory, an atmosphere, oceans, a magnetic and thermal history, an energy flow shaped by elements made before the sun existed. The connection to neutron stars is therefore not a simple claim that life is made mainly of their debris. It is subtler and more grounded. Some of the rare material in the planet, in technology, and in the broader chemical environment comes from neutron-rich catastrophes. The universe that permits ordinary life is chemically enriched by many kinds of stellar death, and neutron star mergers contribute some of the most difficult elements to make. This gives neutron stars a strange double role. Alone, they seem almost hostile to ordinary existence, with gravity strong enough to bend light, surfaces too hot and dense for matter as commonly known, crusts harder than earthly solids, and cores where particles may change identity. In pairs, they can collide in events that tear space-time, forge heavy nuclei, and often leave a black hole where two compact stars had been. Nothing about them resembles a cradle. Yet through the long circulation of matter, they become part of the background condition for later gentleness. Their violence is not softened by this outcome, but it is placed inside a larger cycle. The cosmos does not separate creation and destruction cleanly. It uses the remnants of one process as the starting material for another, often after intervals so long that the link becomes nearly invisible. The journey from neutron star matter to a planet is not a planned path. It is a sequence of physical chances governed by gravity, nuclear physics, radiation, chemistry, and time. A merger must eject material instead of swallowing all of it. The debris must mix into the galaxy. A later cloud must inherit some portion of it. That cloud must collapse into a star system. Solid bodies must form and preserve the elements in accessible layers. Geological processes must concentrate them. At every stage, the setting changes. Nuclear density becomes expanding gas. Expanding gas becomes diffuse enrichment. Diffuse enrichment becomes a cloud becomes a disk becomes worlds. Worlds become places where matter can take on forms unlike the compact object that helps supply part of the inventory. The neutron star itself may persist elsewhere, cooling slowly, spinning down, or disappearing after collision into a black hole. its products can outlive the event in quieter forms. They can move through dust lanes, settle into meteorites, enter planetary mantles, rise through volcanoes, dissolve into oceans, or become part of human-made structures. The extremity of their origin becomes hidden because matter is able to change context completely. A nucleus forged in a kilonova does not remain a cosmic spectacle. It becomes an atom among atoms, obeying chemistry, joining minerals, becoming useful, ordinary, and almost anonymous. That anonymity is part of the wonder. Neutron stars barely seem real because their density, gravity, and internal matter stand so far beyond direct experience, yet their consequences are not confined to unreachable remnants. They enter the slow work of galaxies. They help fill the periodic table beyond what normal fusion can comfortably provide. They connect the death of massive stars, the collision of compact remnants, the cooling of interstellar clouds, and the building of rocky worlds into one continuous material history. The final meaning is not that everything comes from neutron stars, but that even the most extreme objects are part of the same cycle as the most familiar things. A neutron star is a boundary where matter almost falls out of the visible universe. When two such boundaries meet and break open, some of that matter returns. It returns changed, scattered, and patient until the remnants of dead stars become the quiet substance of planets, tools, and bodies moving through ordinary light. The story of a neutron star ends without becoming simple. It begins in balance, in a massive star holding itself open through fusion, and it passes through iron, collapse, nuclear density, supernova light, warped gravity, solid crust, hidden core, magnetic signal, and finally collision. Each stage seems extreme enough to stand alone, yet each one belongs to the same material chain. Matter is gathered, burned, compressed, rearranged, scattered, and gathered again. The neutron star remains one of the clearest reminders that the universe does not reserve its deepest physics for distant abstraction. It builds those laws into objects with surfaces, rotations, magnetic fields, and histories. Some survive as pulsars, spending their spin into space with patient regularity. Some become magnetars, holding magnetic stress in a crust that can break and flare. Some orbit another remnant until gravitational waves draw them together, and the collision releases matter that had almost disappeared into compactness. From that released matter, heavy atoms can enter the galaxy again, no longer as dense nuclear fluid, but as ordinary chemistry waiting for future clouds and planets. The scale softens only after a long delay. The violence fades into dust. The dust becomes part of a new system. The system becomes worlds where heavy elements lie hidden in rock, metal, ocean, and living chemistry. A neutron star barely seems real because it compresses so many limits into one small body: the limit of pressure, the limit of gravity before blackness, the limit of matter before identity begins to change. Yet its consequences are real in the quietest ways. They are carried in atoms, in starlight, in timing signals, and in the slow enrichment of galaxies. The remnant remains distant, compact, and severe. But the matter it helps return is patient enough to become familiar.